Hi there, this is the first tutorial of Chapter 2 of the Digital Soil Mineralogy with R course. And this chapter focuses on quantitative phase analysis from X-ray diffraction data using the full pattern summation approach that's implemented in the POWDR package for R. And this approach basically models an observed pattern as the sum of pure patterns for the various phases that exist within the sample. And it computes phase concentrations using reference intensity ratios. And underpinning this approach is a library of reference patterns of all these pure phases and their associated reference intensity ratios, which are essentially a measure of the diffracting power of each mineral. And there are various various equations for relating reference intensity ratios to phase concentrations, and they're all detailed in the various citations provided in the course documentation. In this tutorial, we're going to be introducing the reference library of the various pure phases and how they are created in POWDR, the form they take, and how to manipulate them in various ways. So to start with, what we'll need to do in this tutorial is load the POWDR package, which is where most of the functions we'll be using come from, and also some of the example data. So to begin with, we're going to load an example data set called Minerals XRD, and you can get help on this just using the standard form, Minerals XRD with a question mark preceding it. And there's a brief description of what the data comprise. So if we load data XR, this data, you'll see that in the top right, we've got our environment and we have minerals XRD and we have this promise value next to it. As soon as we click on the data, you'll be able to actually load it properly. This is just a form of lazy loading that most data loads as in R. So once it's loaded properly, you can click on the data to have a look at it because it's just a data frame of 15 columns and about 1700 rows. And the first column is TTH, which is the 2 theta axis for the subsequent columns, which are all count intensities of various pure patterns that we want to be in our reference library. So this is like the raw XRD data really. And in addition to this, the other information we need is includes what the phases actually are in terms of their mineral groups and those reference intensity ratios. And this is provided in the second table of information. So let's just have a look at an example of this second table loaded using data minerals phases. Again, it loads with this promise message, but if we just click on it, it actually prints the table of information down in your console as well. Let's just load it up here. So we can see that this is also a data frame, as you can see by hovering over there. And it's got 14 rows of 3 columns. So the first column is a phase ID, and this actually matches to the column names in this first spreadsheet we were looking at, first data frame, with the exception of the first column, which is the 2 theta column. So the order of all these IDs matches in both data frames, and we can check that just by using this identical function. So we're going to take the names of the XRD data frame minus the first column, hence the -1. That's what that produces. And we're going to take the first column of the phases data frame, and we're just going to check that they're identical, and we get a true. So that's one of the kind of conditions for creating libraries, that your phase IDs, which are the column names in the XRD data frame, match the phase IDs in your phases data frame. And they all have to be unique. So it's a unique identifier for each of those reference patterns that's going to be in the library. The second column is the phase name, and this gives you an opportunity to define the level of detail that is provided by your library, and it gives you an opportunity to actually have more than one reference pattern for a given phase. So here we have 2 reference patterns for quartz, 3 for K feldspar, 2 for plagioclase, and so on. And the level of detail depends on the quality of your library. If you have very high quality synchrotron data, for example, you'd be able to specify the different types of K feldspars or plagioclase feldspars, but it can be quite challenging to do that from laboratory XRD data, so we group them together. And this grouping will come up later in the tutorials in this chapter. And the final column in this data frame is the reference intensity ratio, RIR. So this is just a numeric value specifying the RIR, in this case relative to corundum. So the quartz patterns have a reference intensity ratio over 4 to 4.5 times that of corundum, whereas organic matter down at the bottom is just 0.07 times that of corundum. So it essentially summarizes the diffracting power of those phases and is ultimately used to derive the phase concentrations. Right, let's just close those data. Now, we've got those 2 pieces of information, and what we want to do is actually merge them into a single object, which is the reference library that will be used by PowDAR to do the full pattern summation. And these reference libraries are simply created using the powdar_lib function in R. And again, get help for that just by using $powdar_lib. So we're going to create this object. It takes the XRD data frame first and then the phases data frame second. And it'll carry out a few checks on the data to make sure that it meets the requirements to become a reference library. So if we run that line, we get an object in our environment called mylib. If we hover over there, you can see that it's a powdar_lib object. And again, you can check that using code. And as we've seen with various other objects there, such as the multi-XY and XY objects in chapter 1, they have methods associated with them. So if we check the methods associated with powdar_lib objects, we can see that there are 6 methods that you can access help on for all of them. For example, if we look at plot, we can do $plot.powdar_lib to get the help for plotting these objects. And you can see that this method accepts 4 arguments. We've got x, which is the powdar_lib object, the wavelength, the refs, and interactive. And we're going to use that to plot some reference patterns from the library that we've just made. So we're going to plot mylib, the wavelength that data were recorded or collected with is copper, so we just add a Cu there. You can also add CO if it's cobalt X-ray source, or you could put in a numeric value to specify the wavelength. The third argument is refs, which gives you an opportunity to define the phase IDs of the reference patterns that you want to plot. So here we're going to define 4 of these, so they relate to these column names in the XRD data frame, or the phase IDs in the phases data frame. And it's actually probably just worth looking at the various items that are within a powdar_lib object before we do this plot. So if we do summary of mylib, we can see that we've got 3 items within this object. We've got XRD, which is a data frame of 14 columns, and we've got 2 theta, or TTH, which is a vector, a numeric vector of the 2 theta axis, and then we've got phases, which is a 3-column data frame. So the phases data frame exactly matches the data up here that we were looking at. The XRD data frame, if we just have a look at that, is almost the same as what we provided to the function, except that the 2 theta axis has been stripped from it. So it's just count intensities. So what we're going to do is, again, going back to the plotting function call. We're going to plot 4 reference patterns here: albite, dolomite, quartz, and goethite. And the final argument that we're going to define is interactive, and we're going to set that to true, which means it'll produce an interactive plot that will come up in the viewer pane if you're using RStudio. And it just gives you an opportunity to zoom in and out of the data and actually get some information about the d-spacings of the peaks, which are computed using Bragg's law, and given that you've provided the wavelength that the data was collected using. So it can take a little moment, especially if your computer is struggling because it's a Monday. But eventually it will load, and we should be able to. Let's just have a look at it here. So this is the data. We've got a plot of our reference library and 4 patterns selected from it. We've got goethite in purple, dolomite blue, albite green, quartz in red. And you can turn various patterns on or off using the legend. And you can have a look at their d-spacings and zoom in, etc. And you'll notice that if we turn all of the patterns back on again, they're all scaled to a same maximum intensity of 10,000 counts in this case, and all of the reference intensity ratios are adjusted for this calculation. And all of the reference libraries we'll be looking at today use this formulation. So that's how to plot a reference library and their basic form. Now we'll just look at a few ways of manipulating them, which includes, well, actually first, before manipulating them, we'll look at some example data that's actually included with the package. And now the data we've looked at so far is just a very small library, just used for examples really. But in addition to that, Powdar comes with quite a comprehensive reference library called RockJock, which comes from the Excel program under the same name, written by Dennis Eberl, and he's kindly provided permission for us to use the data or the reference library included with RockJock in Powdar, which is a really great addition to the software. So if we load RockJock and have a summary of it, we can see that, well, it is a Powdar lib object. It'll tell you up here it's a large one. And it's large due to the fact that it contains 168 reference patterns this time. And the 2 theta axis or scale has a resolution of around, well, it has 3001 separate measurement intervals. And we've got this phases data frame again, which will be 3 columns, but it will have 168 rows for each of the reference patterns. So if we have a look at RockJock phases, this phases table, we can actually see all the reference patterns that are included within the data, and it covers most minerals that will be encountered in soil, sediment, or geological samples. So it's a really useful library. So you can see here it contains about 8 different plagioclase reference patterns and numerous K feldspars. It also has these 2 background patterns that we've added in Powdar. So these are just a flat positive or negative line that, when doing full pattern summation, can account for just constant shifts in count intensities that may be encountered, particularly if you're using data recorded on a different instrument to the RockJock library, which you probably will be. So those can be useful in those scenarios. Now, say we wanted to use RockJock, but we wanted to reduce the library down in size because we're pretty confident that we know what is within our samples, you can use the subset function, which is subsetting powdar_lib object. So you can get help on it again, $subset.powdar_lib. So you'll be able to then get a bit of help on this function and the arguments it accepts. So it will take a powdar_lib object, so we'll provide rockjock, and then you'll define a string of refs or reference pattern phase IDs or names that you want to work with. So in this example, we're specifying 3 phase IDs, which are within the first column of this phases data frame. So they are all unique. So there'll only be a maximum of 1 pattern with a phase ID. So these, we're defining 3 patterns here, but then in the 4th example, we're defining a phase name. And that allows us to actually select all of these plagioclase reference patterns just with 1 addition to the string. So that can be quite useful when using subset. And the last thing to specify is the mode. And this can be one of remove or keep, which is specified there in the documentation. So we're going to remove all of these phases from the rockjock library to produce rockjock1. And so in the first example, in this example, we've reduced the library to 157 reference patterns, whereas before we had 168. So it's removed 11 reference patterns. So it's taken 8 plagioclase and the 3 other phase IDs. Alternatively, if you specify the mode as keep instead, it will do the opposite and it should just keep those 11 reference patterns, which can be checked using that code that I've just run. And again, if we check this, you'll see that we're down to 11 phases now. So these numbers on the left correspond to the row numbers of those phases as they were in the initial rockjock table. Now, in addition to subsetting the data frames, you may wish to merge a couple of libraries in order to create a library that meets your needs. So an example of this is, say we wanted to load a library called Minerals, which is actually produced using this example data that we were looking at earlier. So if we look at the number of phases there, we've got 14 phases in this reference library. And like we've seen already, we've got 168 phases in the rockjock library, and we want to merge these libraries together to produce a reference library with 182 reference patterns. The first thing we need to make sure is that both libraries are on the same 2θ axis. So if we summarize both of these, we can see that at the moment this isn't the case because our minerals reference library ranges from 4 to 70, whereas rockjock ranges from 5 to 65. In addition to that, they're on a different resolution. So if we look at the mean of the diff in minerals slash TTH, we can see that it's got a resolution of about 0.04 degrees 2θ, whereas rockjock has a mean of 0.02 degrees 2θ. So the resolutions are different as well. So in order to get around that, what we can first do is use the interpolate function, which again you can get help on using interpolate.powdar_lib. Just run that. So what this does is it'll take a reference library and it'll allow you the opportunity to define a new 2θ scale to interpolate it onto, and this is using cubic spline interpolation. Here we're going to define the rockjock 2θ axis as the new scale to interpolate the minerals data onto. And once that's done, we can then merge rockjock with the interpolated data and produce a larger library. So now we have a library containing the 182 reference patterns. Now, in addition to the data we've looked at so far, we've got one more example reference library included within PowDAR, which is called AFSIS, and that's a reference library that contains a small number of reference patterns associated with African soils or many soils around the world. So if we have a look at the phases data frame, we can see that it's got a few quartz patterns, K feldspar, plagioclase, amphibole, and so on. And this can be used to enhance the RockJock library, if you like, if you're working with soils. And it's already on the same 2 theta scale as RockJock. So we can check that using this identical function here, which means we don't have to do any interpolation in order to merge RockJock with AFSIS. So you just have to run that single line of code, resulting in a reference library of 189 reference patterns. So that's how to load or create reference libraries in PowDAR and manipulate them in a number of different ways. And these are the basis for full pattern summation that we'll now be moving on to doing. So that'll be in the next tutorial for this chapter.